you very much. It's a pleasure to be with you today. Very happy to speak, even though virtually in Athens. And thank you for coming. So the subject is lifting property for C-star algebras. And you should, of course, warn me if anything goes wrong with, I should have passed to the next page, for instance. So I'm going to start by defining what I mean by the lifting problems. Of course, these are liftings for C-star algebras. So we'll work with quotient of C-star algebras. C over I is the quotient. I is an ideal, two-sided, closed, self-adjoint ideal in C. And A is another C-star algebra, which we will study the lifting problem. So just very general, broad general remarks. First problem is when you have a map U from A to the quotient. Q is the quotient map, and we just want to find a lifting, a good lifting. So of course, U will be, satisfy some assumptions, and we will want the lifting to satisfy similar assumptions. The local lifting problem is a weaker form where what you do is you restrict the map at the bottom to an arbitrary finite dimensional subspace, which of course is we call it an operator space now. So that's a finite dimensional operator space or a finite dimensional operator system. But finite dimensional is important. That's what reflects the term local. And we ask for a lifting just for the restriction to the subspace. So we are not lifting this big map from A to the quotient. We are only lifting the restriction. And so let me insert here an important point, which is that in fact this map here on the subspace, one difficulty is that in the situations we'll be looking at, we don't even know that it has an extension to A. Regardless of global lifting, we don't know that this partial local lifting extends to A. And that's a source of difficulties. Anyway, so this has been studied a lot, and I can't resist really repeating that there is a major open problem that has been open for 50 years, and it drives me crazy that this is still open. It is just for contractions. For contractions, the global lifting problem is open. If you have a contractive U, do you have a contractive lifting U hat? This is open. It's even open whether you have a bounded U hat, which sounds, absolutely incredible. This goes back to work of T.B. Anderson, Ando in the 70s, the last century, and apparently no one pays interest to these problems except a few people who have perverse taste like me. But I find it quite infuriating that this is still open. However, the local problem is well known. It's a well-known fact that if you take, a finite dimensional subspace here, and your U was a contraction, you're going to have a contractive lifting. That's true. That's a consequence of known results. Probably Arveson's principle about pointwise limits of liftable maps, things like that. But this is anyway. This is true. This goes back to Ando, Anderson, and so on. But the global case is open. Okay, so that shows you that local and global are, not the same thing, since here local is very well known, global is open. One little note about, incidentally, the situation for positive contractions is exactly the same as what I just said. Finite dimensional case is okay, that's Westerström. Global case is open for positive contractions. However, of course, the case of Von-Neumann algebras, for those of you maybe who are not so familiar with such questions, so if C is a Von Neumann algebra and everything is compatible with dual spaces, quotient being also a Von Neumann algebra, so the ideal weak star close, then everything is completely clear, because in this case there is a lifting. The lifting is a star homomorphism, and there is no problem. So this is definitely, these problems are definitely C-star algebraic. And the fact that everything simple in the phenomenon algebra case is also reflected by this identity, that when you replace the C-star algebra C by its bidual, which is a phenomenon algebra, then things split. The ideal, the bidual of the ideal, gives a splitting of this bidual. Everything is okay. But let me leave this for later. This will be important only really at the last screen of the talk. Okay, so formally now, the property that we really are interested in is the case where we try to lift unital completely positive maps. So we'll work with unital C-star algebras. It's easy to sort of unitize. So let's leave it unital. U is a unital CP map, and we ask for a lifting which is again unital CP. So that's the lifting property. That's the definition of the lifting property. When it always holds, we say that A has the lifting property. And then the corresponding local case is now called, of course, local lifting property, LLP in short. And it just is the same. U is unital completely positive. E is now an operator system. And we are trying to lift by unital completely positive the restriction to this operator system. Okay. An important thing for the lifting property is that we must restrict to the separable case. The non-separable case is really not well understood, certainly not by me anyway. So let's say separable for definition of the lifting property. And then the unitization is, gives us a definition extended to the unital case. So the problem that has been, worrying me for quite a while now is an open problem that was raised by Kirchberg in his famous Invenciones paper, 1993, is whether the local lifting property for separable C-star algebras, okay, always maybe implicitly I might forget the separable C-star algebras, whether it implies the global lifting property. See, that's very amusing because this question that he asks is actually parallel to the Banach space question with which I started, because in the Banach space question, in some sense, we're asking the same, except that in the Banach space case, by which I mean contraction, lifting of contraction by contractions, then we know the local case is always true. But formally, it's formally the same question. I find that rather amusing. And I have a feeling that both will be answered together. Anyway, the big motivation for this open problem is the Kohn embedding problem, which, for which, as you know, there has been a negative solution posted on Archive now, January 2020, so that's now 2 years ago, by 5 authors, Vidic, G, Natarajan, Wright, and Yuen. And so they claim they have a negative solution, but the preprint is 200 pages long. It's posted on Archive, and it's using arguments from other fields, complexity, logics, computer science. And so although at the moment, the feeling is that, well, this is probably correct, but it hasn't been really verified by, as far as I know, by someone in the community of operator algebras. So that's why this is actually, for me, this is quite important, because what I think is that this is not going to be true, this implication, although, that actually could well end up being wrong. But so let's say I'm hoping that it is not true, and I'm hoping that I can produce an example with the local lifting property and not the lifting property. The reason I think so is that 3 or 4 years ago, I've constructed an example, a new example of C-star algebra with the local lifting property, which was not in, within reach of Kirchberg's paper, of Kirchberg's ideas perhaps, but it's not in his paper. It's a C-star algebra that has the local lifting property, but also a weak form of injectivity called the weak expectation property. And the construction is extremely local, just to give you, an idea of why convinced of these things. The construction being very, very much local, I have a feeling that a modification of these examples, it's a class of examples, really, a modification will end up failing the lifting property. That's my dream, that's my great hope, and I've been working a lot in vain trying to do that throughout the confinement of the COVID and so on. But anyway, that's the reason why I became very interested by the lifting property, and why I tried to produce, characterizations of the lifting property, LP, which could give me a tool for the project that I'm describing now. I want to construct algebras failing the lifting property, so I need good criterion for that. And I will show you in the end a characterization of the lifting property, which I've been hoping to use for that project. So let's talk about some examples. So of course, the examples of C-star algebras with lifting property, as I'm sure all of you have heard, include the nuclear C-star algebras. This was proved by Choi Efros, a celebrated paper in Annals of Mathematics, 1977. So that's C-star algebras of all, amenable groups. So this class of C-star algebras with lifting property includes, that's Kirchberg's theorem, the full C-star algebra of any free group. So, Z, of course, but that's the amenable case. But Fn for, at least two generators, as you know, is not amenable. The C-star algebra is definitely not nuclear. It's a very different example. It's an algebra when when the free group has infinitely many generators. It's an algebra that has any C-star algebra, any separable C-star algebra as a quotient. And so that's a universal object for quotient C-star algebras. And it somehow is, the fact that it has the lifting property for me is analogous to the fact that in Banach space theory, little L1 has the lifting property, a certain type of lifting property. But anyway, so we'll discuss full C-star algebras mainly in the talk. I just mentioned in passing that some things are known about the reduced case, which sort of make us disregard the reduced case. For instance, it's very well known that the reduced C-star algebra of the free groups will fail the local lifting property. So the sharp contrast, the full one has the lifting property, the reduced one does not. Okay, another important fact that must be mentioned, and it gives the impression that you don't need to know anything more about the lifting property once you say what I'm going to say, but I'll explain why this is not quite true. So any separable C-star algebra is a quotient, as I just said, of C-star F infinity. So your A is itself a quotient. So the first thing that you will want to lift, if you're interested in the lifting property, is the identity map, because the identity map now is a map into a quotient, since your algebra is a quotient. And if you can lift the identity map, then diagram chasing will show you very easily that, okay, you can lift anything. So the lifting property follows just from the identity map, and the identity map is a star homomorphism. So that gives you, an equivalent definition of the lifting property. You could say, well, it suffices to be able to lift. Lift now will mean always by unital completely positive maps. It's enough to lift any star homomorphism from A into a quotient. And in fact, it's enough to lift one, which essentially is the identity. And that's the same for locally liftable. But if you think of the analogy with injectivity, injectivity, nuclearity develops a very, very powerful theory with all sorts of questions. And knowing that injective phenomenon algebras are those that are embedded in B of H with a contractive projection onto them is not the end of the theory of injective phenomenon algebras, as of course I'm sure you realize. So having said this, that that these algebras with lifting property are those which can be realized as a quotient with a lift. And you know that if there is a lift, there is a projection onto the kernel and so on, so forth, all sorts of things. Well, this is not the end of the story. That's what I mean. It's of course very important fact, but it's like the first base. So of course we can introduce for a discrete group the lifting property and say that discrete group has the lifting property if the full C-star algebra has the lifting property. So we have this strange class of groups that includes amenable and free groups at the same time, which is a little bit unusual for properties used in C-star algebra theory. And of course, it is not so easy as a consequence to find counterexamples, because usually, if you want to find counterexamples outside amenable groups, the first thing you try is groups containing free groups, and well, that doesn't seem to be the right direction here. As far as open problem, it's a major open problem. It was raised by Ozawa, whether the product of two free groups, non-trivial free groups, have the local lifting property or the lifting property. Both cases are open. This seems to be closely related to the embedding problem. Okay, there's a discussion. I refer you to Ozawa about this. Examples to the lifting property. So as I said, it's not so easy because of what I just said. All the counterexamples so far have something to do with Kazhdan property T. So the first one was given by Ozawa. It was a non-explicit construction that produced, by using cardinal accountable, somehow he proved the existence of a group such that the full C-star algebra fails the lifting property, but he didn't get it explicitly. Later, Andreas Thom produced a very nice example, explicit failing the local lifting property. Both groups have property T. And more recently, Johanna Spass and Wiersma showed that the usual classical groups that are known to fail property, to have property T, sorry, I might have mixed up, that have property T, fail the local lifting property. So SL and Z for n at least 3 fails local lifting property. Of course, not for n equal to 2, because then we are back to a group that looks like a free group and it has it. So it's still open for general property T groups, whether this is true. And another very nice result which they showed, which I find very striking in particular for my project T, and is not finitely presented, okay? So finitely generated and determined by finitely imposing finitely many relations on a free group. So if it's not finitely presented, then the C-star algebra, full C-star algebra, cannot have the lifting property. It fails the lifting property. And so this is quite nice, because they also show that the collection, the uncountable collection that Ozawa initially considered in his initial paper on this slide, all these groups that form an uncountable collection, they actually are like that. So they fail the lifting property. So you have really many counterexamples, and not so many positive examples, because in fact, outside of amenable groups and free groups, positive examples are also failing. So hence this question, and the simplest group product of two free groups is open. So you can see situation is actually, the information we have is still very, very frustrating, very limited. So I now will talk about tensor products, and I started by reminding you just a list of names, important names of people who founded the theory of tensor products of C-star algebras. Of course, that was at the time when Grothendieck was developing the Banach space tensor products, and then in Japan it was developed by Turumaru, Takezaki, a little bit by Guichardet in France, and important work by the names that you can see here. Lance, Choi Efros, Kirkberg, Efros Lance, Hagerup, Archbold Batty concerning local reflexivity, and Kirkberg. All these people produce results that have something to do with what will happen at the end of the talk. So for those of you not familiar with tensor products, Aristides, I think it's probably good that I just redefine minimal and maximal tensor products. If not necessary, you tell me.
Of course, yes, do.
Okay. So yes, so we have the tensor products that are obtained by completion of the algebraic tensor product. So I diverge from the tradition. For me, A tensor B is always the algebraic tensor product. And we have on two C-star algebras A, B, the algebraic tensor product, we have two norms, which are the minimal norms with which we can define a C-star algebra, and the maximal norm with which define a C-star algebra. And they are defined like this. The minimal norm of an element T is just what is called the spatial norm. So you look at A and B realized in B of H and B of K, and you introduce the natural action of your tensor on H tensor K, compute the norm, and that's the spatial norm. And the maximal norm is the supremum of the norm that you obtain by representing A and B on the same Hilbert space, H. So that's no longer a tensor product Hilbert space, that's the same Hilbert space, and just requiring that the ranges commute. And then the soup over the norms that you obtain is the largest possible C-star norm. There are two other products that play a role. I will mention them later, so I wanted to define them. These are variations that are less well known. They were introduced by Efros Lance. And so if one of the two, let's say A is a phenomenon algebra, so if A is a phenomenon algebra, then one can introduce the normal C-star norm, which is like the max, exactly like the max, but one of the two representations, the one on A, is restricted to be normal. You restrict to normal representations on A. And if they are both phenomenon algebra, you can introduce the binormal C-star norm, which is obtained by just souping over both representations being normal and always commuting range. So that gives you a nice thing, which is that when you complete the algebraic tensor product of the biduals with the binormal, then this sits isometrically and somewhat canonically in the bidual of the max. So you have a good picture for tensors that are controlled in the bidual of the max if you introduce this binormal. That's one of the motivations. So of course, I'm sure many of you have heard, so any C-star algebra will be sandwiched between the min and the max. And so after completion, we have the minimal and the maximal tensor products. And the classical definition of a nuclear C-star algebra, of course, is that it's one algebra, A, such that, well, there's always only one tensor product with any other C-star algebra. So A tensor min C is identical to A tensor max C for any C. So that's the case where this sandwich, become just reduced to a singleton. Two very important identities should be emphasized. They emphasize the difference between the minimal norm and the maximal norm. And this is crucial for the discussion we're going to have. So the minimal norm is, this is well known, and it's obvious from the definition, more or less, it's injective. So the minimal tensor product when B is included in C of A tensor B is included in A tensor C injectively and isometrically, right? I remind you that with C-star algebras, C-star morphism, injective is the same as isometric. However, for the max, the analogous property is not injectivity, but projectivity. So if you take the max tensor product with a quotient, then you can identify it with a quotient of the max tensor product. So I call this projectivity, which I think is reasonable. And the important thing is that the reverse properties are not true. So the max tensor product is not injective. So it's important to see that here, this is not true. And here, this is also not true. The min tensor product is not projective. And this creates specific difficulties for the theory with the minimal tensor product and the theory with the maximal tensor product. And I'm going to emphasize maybe some parallel between the two. So Kirchberg's characterization of the local lifting property is a very pretty theorem for which actually I gave a much simpler proof in a paper in 1996. But it says that you can characterize the local lifting property by just saying that the C-star algebra, A here, gives you the same tensor product when you tensorize with any B of H or any injective, okay? Or if you like, you could say, this is elementary to pass from one to the other, you could say that you can tensorize like this in a single way, min being equal to max, when B is this object here, which is the notation for the direct sum in the L infinity sense of matrix algebras Mn, the direct sum running over all sizes, so sum over Mn. So that's denoted product of Mn in the C-star literature, but somehow I can't conform to this tradition. For me, the product is product of sets, and that bothers me. But anyway, so the Banach space notation that's sort of admitted is this one, and it's sort of more convenient for me. So we have a tensor product characterization of the local lifting property. And so you can see why what I'm going to discuss next was natural for me. I tried to produce a tensor product characterization of the lifting property, of the global lifting property. And in fact, this came somehow rather late for me because I didn't think this existed. I didn't really believe this existed. This was not in Kirchberg's series of papers on the subject, and it seemed rather, unlikely, because you would think that local properties are those which have tensor product characterization, not global properties. And as you will see, that's not quite true. So anyway, let me first discuss a little bit the stability properties, because this is interesting and somewhat could turn out useful. So the obvious stability that you have is, finite direct sums or extensions. These are fairly standard because the definition with tensor products gives you that. Something that's less clear, but is true, and it's satisfying because it reflects the analogy with L1. The LLP and the LP are stable by full free products or maximal free products for arbitrary families, okay? And for the lifting property, this was proved by Boca in 1996, and it's actually a quite easy consequence of his own theorem from 1991, which is a very important fact that says that you can sort of define, and it works, the free product of unital completely positive maps. And it produces a new unital completely positive map, which is like the free product of the maps. And then if you know this, then the proof that the lifting property is stable by free products is just in front of you in the bottom part of the slide here, because you use the fact that it's enough to lift star homomorphisms, right? It's enough to lift what I abusively called the identity, okay? So it's enough to lift the identity. So assume you have it for any I. So for any I, you have found a lifting UI like this. Well, just now take the free product of all these diagrams. And then you have no problem with the quotient maps. These are star homomorphisms. You have no problems here. You have no problem, of course, for the identity. And so Boca's theorem tells you that, oh, it's okay because the free product of this UCP maps is UCP. And then, of course, since it's defined in a canonical way, of course, it makes the diagram commute. So that's the proof. Okay. So another obvious stability result is that if your identity, if the identity of A factors through C with decomposable maps, so I'll talk about decomposable maps in a second, that means linear combination of completely positive maps, then the lifting property of C or the local one passes from C to A. So this is inherited from C to A. And another property, which is easy from the tensor product characterization of Kirchberg, is that if you have a nested family of C-star algebras and you look at the inductive limit or union, closure of the union, the familiar construction, if each of the AIs has the LLP, then A has the LLP. I like to emphasize this one because, in fact, it's not clear for the lifting property. And you see, this closure argument requires some kind of approximation, which of course is easy to do with finitely many elements. But if you're dealing with a global lifting, then there's a problem. So there's a problem. This doesn't look true, and that would be, that's like a clue, I think, to try to show that the implication local to global fails. But I couldn't use it so far. Okay, so now I come to this new characterization of the lifting property. And so I'll explain what it is, but let me first say that it is in the yellow box. So that's really the main result. The yellow box, it tells you the lifting property is characterized by, in some sense, an inequality. And already that's a little bit surprising that, just an inequality characterizes the lifting property. So the inequality is like this. You take any family of C-star algebra as DI, that can be simplified. But anyway, any family of C-star algebra as DI, and you look at the direct sum in the L infinity sense, you tensorize with A. So this is, remind you that this is the algebraic tensor product. So this T has sort of finite rank. And so obviously any such T by projecting will define, it has components, Ti, which each are in Di tensor A for each I. And so you can write the soup of the max norms, and the identity which expresses the lifting property is that the soup of the max norms actually controls the max norm with respect to the L infinity direct sum of the DIs. So it is an inequality. It is an inequality. That's the inequality that matters. So that's why I describe it as an inequality. But in fact, it's going to be an equality when it holds, because the reverse inequality is trivial. The reverse one is obvious. If you control the soup, you control individual terms. That's a familiar thing that we use all the time. And so the property star means that the tensor product with the L infinity direct sum embeds isometrically in the L infinity direct sum of the tensor products. So it can be described like a commutation. It's a commutation of the operation max tensor product and L infinity direct sum, which seems like something rather nice property to sort of pinpoint. One thing to observe immediately is that in parallel, if you now look at the minimal norm is the spatial norm. This is, of course, obvious for the minimal norm. This is always true for the minimal norm. This is quite clear. So So for instance, it gives you, since it's trivial for the minimal norm, you have, if you know, once you know that this is the lifting property, it's trivial that a nuclear C-star algebra has the lifting property, because, a nuclear C-star algebra will have min equal to max with anything. And so nuclear C-star algebras obviously satisfy this. So the with this tensor product picture, this theorem is very clear. Now, that I'm going to use is I'm going to use things very much like operator space theory, but I'm going to use, instead of the minimal norm, I'm going to use the maximal norm. So I introduce the following definition. So E being a closed linear subspace of A, or an operator system if you prefer, but let's say closed linear subspace, let's say an operator space, then we define the max tensor product of D and E. So D will always be a C-star algebra, A, D, C are C-star algebra, E will be reserved for operator space. So this is the closure of the algebraic tensor product of D and E in the max norm inside the max tensor product of D and A. So fine, is good. We have a good definition, okay. And of course, we could reverse the roles. So I define also E tensor max D. It's what I was doing on the left, I do on the right. I put A on the right, and this is the same. However, one important thing that immediately must be emphasized, and it explains why this hasn't been used all over the place, is that there is an abuse here. This tensor product of D and E doesn't depend just on E. It really depends on the embedding of E into A. And so the containing algebra actually determines this norm very much and determines it essentially. So as I emphasized earlier, the max tensor product is not injective. So if I change A by enlarging A, replacing A by a larger C-star algebra that contains it, it will spoil the max tensor product. Not spoil it, it gives a different tensor product of D and E. So one has to be careful always with reference to which embedding this is meant. So that's a problem, but for the analogies that I want to discuss, it's good to have this notion. Okay. So is this already here? Yes. Okay. So this is already here. So let's prove something. This way, I will have proved a result, and the other results I won't have time to prove. But this can be proved fairly reasonably, fairly quickly. Just one implication: why does the lifting property imply this? This special property of exchange between max tensor product and L infinity sum. So here's how you do it. Just look at your A realized as a quotient C-star algebra generator. We're talking always A separable. And now we consider, so I ask you to remember what I said initially. So we are assuming that A has the lifting property. So A is now a quotient of this C-star algebra, but it's liftable. It's a quotient which is globally liftable inside the C-star algebra by a unital CP map. Yes, sorry, I was myself missing my logic and got confused. So if you think of what it means, since the identity of A now factors with unital CP map through the C-star algebra C-star F infinity, it suffices to prove this implication for that C-star algebra, C-star of F infinity, because that you will chase the diagrams, and that's very easy. So in fact, that implication just boils down to the fact that this C-star algebra satisfies this, which is true, but not completely straightforward. So why is it true? Well, now I look at this C-star algebra. It's the same to look at an arbitrary large number of generators. Assume that we have n-1 generators. We stick in the unit, so we have an n-dimensional space En that sits inside C star F infinity, the UIs being the free generators. It's well known that this is, the operator space version of L1, sometimes called max L1 of dimension n. And so by arguments which are the same as what I used in this proof of Kirchberg's theorem that I alluded to, I've introduced a certain type of linearization trick that allows to show this. By this linearization trick, it suffices to show the inequality, the inequality that corresponds to star, suffices to show it not when you tensor with A, but just when you tensor with the unitary generators, the linear span of the unitary generators, which in this case can be just reduced to these. Okay, so we need to show, what do we need to show? Let me show you what goes on. So we need to show in the end that if this soup is less than 1, then the conclusion here is also true that this soup here, this last bottom norm, is less than 1, because that's exactly what expresses, the inequality that is needed for this to be isometric, the non-trivial inequality. Okay, so the funny thing is, I've been trying to sort of work more on this idea, but it seems that what's essential here is that there is a formula. There is a formula for the max norm with these free generators, and there's a formula that is a formula of a certain type. And whenever you have a formula of the same type, the proof works. But I have not been able to actually give well, there's something in my paper that develops this, but I couldn't find a good illustration with an example, except for the free groups like here. So here we have a formula. What is the formula? The norm of this guy, the max norm of this guy, is exactly the same as the infimum of this product whenever you look at factorizations of xj as a product, aj star bj, product being done in A, the algebra A that you're looking at. Sorry, the algebra is D, is the algebra D. D are the coefficients here. En is the unitary generators of A, which turns out to be the full C-star algebra in this case. So assume that the soup for each coordinate is less than 1. So that means for each coordinate, you can factorize, and you can factorize with this bound because we have this formula. But now we want to factorize the family xji in the L infinity direct sum. But that's a trivial thing to do. We just write pointwise factorization, which we have here, and we just say, well, pointwise factorization is the same in the L infinity direct sum as the factorization of xj as aj star bj. And then the norms that of these guys computed in the L infinity direct sum, they're just the soup over i's of the norms. And so this will follow. Maybe I'm forgetting a small thing which has something to do with homogeneity. It's possible that I'm forgetting that I can also, by homogeneity, assume that this norm and that norm, not only their product is less than 1, but they're equal. So each of them is going to be strictly less than 1. And then I can write that, their soup, the soup of this family is less than 1. The soup of this family is less than 1. I think I might have just forgotten it. That's a minor thing. But so that's how the proof is done. That's how you show that the inequality implies the lifting property. So that's gives you, by the way, modulo the modulo the rest of the paper, it gives a different proof that the full C-star algebra has the lifting property, which Kirchberg proved by a rather involved and sort of not so simple argument.
And there's a question, Gilles, I think, in the chat.
Yes, go ahead. Yes, I'm
waiting. Go ahead.
There's a question in the chat. You want me to look at the chat? let's see. Help, no, hello.
Little n and big N.
Oh, little n and big N. Okay.
Okay, okay. Yeah, thank you. Okay, so the tool that I use, which I tried to present, emphasizing the analogies, is maximally bounded maps, which in short are the same as completely bounded maps, but just when you replace the minimal tensor product by the max tensor product. So you will look at maps from an operator space E sitting in a C-star algebra, so given together with the embedding of E in A, and the map goes into another thing like that, or just the same, a C-star algebra, C. So the map is called maximally bounded if it tensorizes with any other C-star algebra for the max tensor product, and of course for the max tensor product on both domain and range. And so then, we can just follow, the imitation with the operator space theory. So we denote MB of EC, the norm space of such things, and we could also define, and this makes sense. It seems interesting in some questions, the maximally positive maps when E is an operator system. And this also depends on the embedding because there's some closure issues, and the positive elements depend also on the embedding. Okay, now a little bit about decomposable maps. So decomposable maps from A to C, A and C being C-star algebras, are just linear combinations of completely positive maps. Completely positive maps forming a cone. Of course, it's going to be a linear combination of 4 completely positive maps. And like this, like indicated in this formula, so all terms, the 4 terms are completely positive. That's the definition of a decomposable map. What's a little bit non-trivial with decomposable maps is the norm. So I will use the norm of decomposable maps, and I will just not write for you the definition. The correct definition is introduced in Hagerup's paper in 1985. And it's very simple if the map is self-adjoint, and a little bit more involved in if it's not self-adjoint, you have to make a reduction to self-adjoint, matrix trick, and so on. But for self-adjoint, it's just like for measures, very simple. It's the infimum of the norm of V1 plus V2 whenever V is the difference V1 minus V2 of 2 completely positive. Okay, so that's decomposable norm. So that's it's clear. And Kirchberg had a result that's unpublished, but that he allowed me to publish in my book. Actually, it's in each of my 2 books on operator spaces or tensor products. And so it's a result that says that, well, the situation is exactly the same as the decomposable norm of U, provided you embed the range C into the bidual. So this IC is the inclusion of C into the bidual. And in fact, what I'm using is a refinement of his result. When I worked out, the proof of his result for my books, I just noticed that actually there seemed to be a very interesting generalization that was like, Han-Banach looking, just like at some analogy with, how do you say, Arveson Han-Banach theorem for maps into B of H and so on for completely bounded maps. So it says this, that for a general maximally bounded map, now on the subspace E, so E is a subspace of A, the maximally bounded norm is just the same as the infimum of the deck norm of the extensions, all possible extensions of the map U, provided you go into the bidual. So it is the diagram that's relevant is this one here. We have U and then U tilde, which I call the extension, but this is abusive because it extends with enlargement of the range. So the infimum of the deck norm of this U tilde gives you exactly the MB norm of U. So the main result, I actually sort of got carried away when I noticed that I had this equivalence with the lifting property, and then I couldn't resist. I played, all the variations of the games that one could play, imitating the things that we know with the minimal tensor product. So I have all sorts of properties that are equivalent to the lifting property, and that are, I can claim they're sort of nice sounding. Okay, so let me check time now. I see that why are we doing with time? Okay, I've passed, I think, past 50 already. So I guess I can have a few more minutes. Aristides, I think I'm at 50 minutes now.
No. Yes, of course. You can have more minutes. You can have more time.
No, I'm not. More. Okay, I'm confused. Okay, so we have a lifting property. We know what that means. Property star, we know what that means. It is this inequality. The third one is an amusing one because it is analogous to local reflexivity. It is analogous to local reflexivity, but for this maximally bounded norm instead of completely bounded norm. So for any finite dimensional subspace E in A, we have here this embedding contractively. And if you put the minimal tensor product instead of the max, you get, local reflexivity. Similarly for property 4, and property 5 is just a variant where you consider the max tensor product of A with a von Neumann algebra. So here M is a von Neumann algebra, and then the property consists in stating the identity of the max norm and the norm, normal tensor product of M and A, of course, meant on the left where the von Neumann algebra sits. This, I should say that this property was considered by Kirchberg in his main paper on the lifting. And he claims that, he proved, that's one of his theorems, that the full C-star algebra satisfies this. So he claims that lifting property follows. Lifting property implies this property number 5, and then says nothing on the converse. So unless I missed it, I pretty much looked at all the papers. I don't think he says anything about the converse, and that whole set of that property star somehow gives it fairly easily. If you see it with 1 equivalent to 2, you sort of get to this one fairly easily. But anyway, so I should say he had seen that 1 implies 5. Okay, then 6 is a commutation which is also a little bit strange between ultra product. This time it's ultra product of C-star. Okay, it's a C-star algebraic tensor ultra product. So you take max tensor product with the ultra product. You cannot have an identity because, as you know, the ultra products are always huge. They are huge spaces, so they're not going to be generated by finite rank tensors. But that's what this says. If you look at what is generated by finite rank tensors, then the norm of this guy is the same as what you obtain by forming the max tensor product. This one is interesting because, or I'm not sure that makes it interesting, but that makes it rather amusing, say, because for C-star algebras, that looks like exactness. If you put the minimal tensor product, that's very close to exactness. So if the DIs are operator spaces, this is the same as exactness. So here I've repeated, I want to make more comments on the first 3. I think it's good, I'm not so far from the end, so I might not go over too much. So the first 3, I've selected the comments to make complements on the first 3 properties, in particular that third one. So that third one is the one that looks like local reflexivity. So for this one, the main point is 2 implies 3. and for 2 implies 3. So we start with this inequality about commutation with L infinity and max tensor product. So we have this, the space, of course, of maps MB naturally comes up. The point is that one can make an analysis of the dual of the space MBEC, which is particularly nice when the algebra has the property star. So I'm not going to really say what it is. I can't sort of go into too much detail, but so we can introduce for E finite dimensional, say, for E finite dimensional, we can introduce the alpha tensor norm, which is defined by this identity, by this isometric identity. And then the point is, if you have property star, you have, how to say, precisely the ingredient that is needed to analyze the bidual. So once you know the property star, you have a property of alpha that gives you a description of the bidual of this guy, from which this follows. So I could say this is a bipolar argument by convexity, bipolar, modulo the use of the property star. Okay. And another formulation of this importance of the local reflexivity property is this. So that's one more variant. And this is sort of reminiscent. Some of you might have sort of played with this also for completely bounded maps. So 3 prime, which is equivalent to 3 now, I formulate it without using finite dimensional spaces. So it's the same thing as saying that any MB map, something is missing, of course. Any map in MBAC double star can be approximated pointwise weak star by a net UI in the unit ball. So of course the original one should be in the unit ball. I forgot. So U should be in the unit ball here of this space. Then it is pointwise weak star approximable by a net of maps in the unit ball of this. This is another way to formulate the property LP. I think I reached the end of what I wanted to say. Thank you very much. The last page is an advertisement for my book, which is, this is a sad, it's one of these sad things that the book appeared and it's really devoted very much to the Kohn embedding problem. I call it the Kohn-Kirchberg problem because Kirchberg developed the C-star version of Kohn's problem, which is a phenomenal algebra problem. And the book appeared very much at the same time as the preprint claiming to have the solution appeared, but it could not be mentioned, of course, in the book since that was too late. And also it could not be mentioned in the book because, of course, I would have had to understand the proof. And 2 years later, no one has still understood the proof, although I should say honestly, the buzz is that it's probably correct. Thank you very much.
Okay, thank you very much for the talk.